So welcome everyone to this session. My name is Sebastian, and I'll be speaking today about sustainable software engineering in Azure Data. My role is right now as a software engineer on the Azure SQL Database team for Microsoft, and I come from Mexico on Monterrey, which is a city in the northern part of the country. Just as a fun fact about me, I'm an amateur runner. I'm training for my first marathon. So if anyone besides data is also passionate about running, make sure to connect with me. With that, let's go ahead and get started. So let me explain why this topic is interesting and resonated with me when I got to it. As I started my career, I was standing behind the computer for 40 or more hours per week, and I was thinking, okay, is this everything that is to life as a software engineer, as a person who is involved with technology? And that's a question that was in my mind constantly. So I wanted to find a way in which my work could not only help people build more powerful tools or to create better applications. I wanted to have a major impact on the environment. So as I started looking for ways to do this, one of the problems that most resonated with me was global warming and climate change, which is something that we all have heard before. It's a problem that affects everyone in different ways, but I wasn't sure there was an actual connection between me and that problem. My first thought was, okay, this is a problem that's being caused by big factories, big companies producing items on far away from where I live. But actually, there's something that links us, or personally me, and this problem, and that's the constant use of electricity. And that's something that we cannot avoid at all. It's intrinsic in our day-to-day work. We use it for entertainment, for daily tasks, even for washing our clothes. We need electricity, and the way in which we use it is not always the most efficient. So with this idea, I came and discovered sustainable software engineering as a new discipline, and that's why I want to share this information with you, share what this is all about, and maybe it motivate you to start digging on it so that you can learn more and come join the community that's growing on this new discipline. So for today's agenda, we will start with what is sustainable software engineering. I already gave you some pointers, but I want to have an actual definition of what it is. After that, I'm gonna present to you all the 8 principles of sustainable software engineering. These are principles that the community has created to move and push at a change in the way we design things and we architect applications, to use more sustainable or environmental friendly techniques. And the third big pointer, the third big topic on the presentation is serverless as a green design principle or a green design pattern that we can use and leverage from the cloud. We'll talk a little bit more about what what serverless is and how serverless can be used to move our applications into the cloud and use the resources in the most efficient way. And at the end, we will talk about Contoso car insurance company, which is an insurance company that I just invented for this presentation. And I want to share with you a way in which we can move an on-premise application to a cloud application. We'll see how that works at the very end of the presentation. So with that, let's go and define what is sustainable software engineering. So this was created as an intersection of existing disciplines such as climate science, software engineering, electricity, electric engineering, hardware design, and data center design. So as you can see, almost every person involved in technology in some way could be part of this new discipline. The idea is to be conscious about the carbon that we are emitting with our day-to-day activities, and as we said, to change the design thinking by leveraging the cloud and shift our, if possible, shift our workloads from our local servers to and use some cloud provider as a solution. These principles, this discipline is pretty new, and people from different companies, different sectors is trying to build up the new steps for it. So as we're gonna see, there's 8 principles that will help us understand a little bit better how can we actually start implementing and start using this discipline on our day-to-day tasks. The first one is carbon. This principle is all around creating carbon efficient applications and services. We know that the greenhouse gases, the problem with the global warming is caused by greenhouse gases being emitted to the atmosphere. Not only carbon dioxide is the one that causes some problems, but there's also other ones such as methane, which could be potentially more harmful than carbon. The idea of having carbon as our first principle is that we want to normalize all of the other greenhouse gases into an equivalent impact to the environment. This is important because we can actually measure the impact of our applications, our services, our workloads in the same language, instead of saying, okay, this produces X greenhouse gas or Y greenhouse gas. We can just say, okay, the carbon that's being emitted is, or the carbon equivalent that's being emitted is X amount. And as we will see on the other 7 principles, carbon is the foundation to the rest, because we want to, at the end of the day, reduce the amount of carbon that we emit so that we can stop or diminish the global warming. So with that, let's go to the second one, and which is electricity. For this one, it's easy to be fooled thinking that it's not so harmful to the earth. When you actually plug your computer or you're charging your phone, there's no dust or byproduct coming out of the socket, right? So at first, I myself was thinking, no, okay, the electricity is a pretty clean source of energy, right? However, the big problem here is that non-clean production of electricity is that most of the electricity comes from non-clean production. Fossil fuels such as coal and gas are the main sources still on the world today. And only some specific countries have managed to flip the production of electricity to use as a majority renewable sources such as sunlight, wind, or even water. So the idea is that we create energy efficient applications that for every kilowatt that we need to extract from the grid, we take out the most work possible. And it's important to mention that kilowatt hour is the standard way in which we measure electricity and energy throughout the world. This will be relevant to define the next principle. So the second one is create energy efficient applications. The third one is related to carbon intensity. And we already mentioned that there are some clean ways to produce energy and some non-clean ways. The idea is that not every kilowatt that comes to as power on the grid is going to have the same environmental impact. The production of energy varies depending on the region and also changes depending on the time of the day where you're producing the energy. The companies that produce this energy need to keep up with the demand that a certain region or a certain city is having. And even when there's maybe a surplus of clean energy, they cannot store it, or when there's a shortage of energy, they need to compensate by burning more fossil fuels, and this could be a real difficult problem for these kind of companies. As the standard unit that we use to measure the carbon intensity of energy is grams of carbon equivalent per kilowatt hour. And as we mentioned on the first principle, not every greenhouse gas is carbon. So we need to translate every other greenhouse gas to carbon, and that way we can measure the damage or the impact that it is having on the earth. Just as a utopic example, if we could plug our computer into a wind farm or like a eolic farm, the carbon intensity of that energy will be 0 grams of carbon dioxide equivalent per kilowatt hour. But we know that that's not actually possible, or it's not really easy to do, not practical. A way in which we can use the carbon intensity to be more sustainable is by using a technique called demand shifting. And demand shifting is the idea of moving workloads from one time frame to another, or from one region to another, where the carbon intensity is lower. So to see this on a graph, we can see that as demand is staying the same throughout the day. We have a graph of time, and the demand is remaining at the same level. However, on the first pile of energy, we see that there's only 120 grams of carbon dioxide equivalent per kilowatt hour, because most of the energy is coming from wind and solar. And as time passes, the wind stops blowing and the sun stops shining, and now this lack of clean energy needs to be compensated with burning more fossil fuels, and the carbon intensity doubles and goes even above the double of what we saw on the first pile. This is the issue with carbon intensity of energy. So the idea is create applications that use electricity or energy with the least amount of carbon intensity possible. That's the third principle. With that, we go to the fourth one, which is embodied carbon. And embodied carbon is or measures how much carbon pollution was emitted during the creation of a certain device. Our smartphones, our tablets, or even the laptops and servers that are running on the cloud, all of these devices emitted some carbon and some pollution during its creation. We need to account for this when we are measuring their impact on a yearly basis. And you would say, okay, maybe this is not so relevant. And that was my first thought. I said, oh, how much carbon can a cell phone have, or a computer, or even a server? My first thought was that the real impact that a device has is coming from the energy that it uses on its day-to-day tasks. However, something really relevant here is that embodied carbon for some devices accounts for the majority of its yearly carbon impact to the environment. So extending the life of devices as much as possible is something that we as engineers, or in general people who is working with technology, needs to have in mind when designing maybe a new data center or even workloads, because we're tempted to keep increasing the complexity of our workloads so that only the newest generation of hardware can run it. We want to optimize time as much as possible, and the hardware, which is not so new but it's still in a good state, can keep up with these workloads and gets disposed even before it breaks down. So just to show you an example of how this could be seen on a hypothetical server, we have this server which released 4 tons of CO2 when it was created. That means that if the lifespan of this server is 4 years, we need to account for 1 ton of CO2 per year, and then it will be just a pile of metal running around. If we manage to extend the life of this server 1 more year, the impact per year of the embodied carbon will be 800 kilograms of CO2 per year. And you can see that this is relevant because once you dispose the server, you will potentially buy a new one, and that newer one will have some embodied carbon, and this is a non-stopping calculation that you need to be taking into account. And 200 kilograms of CO2 per year per server is actually something that could slow down in a really high way the impact that a server fleet can have. Imagine if this applies for a cloud provider which has thousands or tens of thousands of servers. So these are the four principles, the four third principles, and I just want to go over them real quick. So the first one is create carbon efficient applications. The second one is create energy efficient applications. The third one is create applications with the lowest carbon intensity. And the fourth one is create applications which use hardware in an efficient way. With this, let's go to the fifth principle. The fifth principle is energy proportionality. And the idea of energy proportionality is to measure the relationship between the power consumed on a computer and the useful work that's being done on it. This is also known as utilization. And the higher the utilization, the more efficient the use of energy becomes. And the problem with the power being drained by a computer is that even at 0% utilization, the hardware still consumes energy. This sounds a little bit weird at first, but we can see it on this graph. The blue line marks the power being drained by a specific server, and this blue line never crosses the origin. The problem is that there's static power that a server or a computer needs to be draining from the grid to just to keep the components on. And as you increase the workload to 50% or to 100%, this blue line doesn't increase linearly. So in a way, having a server running at the 50, 60, or if possible, 100% of its utilization, it's ideal instead of having, let's say, 10 servers running at the 10% of utilization. The power consumed will be much higher if you think it this way, and the impact will be much lower. And just as a fact that came around 2015, it may be a little bit old, but it helped us. It gives us an idea of how this could impact in the environment. A company that has an on-premise architecture and that has like its system running on-premise has an average utilization, an average yearly utilization of its servers of just 15%. This compared to a cloud provider, which could go up to, its average goes up to 50 or 60% annually. So as you can see, maybe the same hardware is being used on both the cloud provider and the on-premise side, but they have a very different utilization and a very different impact to the environment. The principle number 6 is networking. And this also sounds a little bit strange to me at first, since networking is something that we're so used right at the moment. It's so natural to just wake up and start sending emails, checking social media. We don't even think, or normally we don't think what's the infrastructure behind all of the bits that are flying through through the internet, through our cell phones, through our devices. However, the reality is that the network is built with hardware devices. And what do these devices need? They need energy to function, right? So any bit of information that's traveling through internet emits some kind of pollution, emits carbon in a certain way. And it's true that not all of these devices have the same impact. Not all of them have the same carbon intensity. And it is actually really hard to measure the impact of a message that you send through internet, because maybe it will need to travel different distances depending on where your receiver is located, or also depending on the number of hubs that your packet needs to travel to reach their destination. There will be different carbon intensities on the region where specific routers are located, and even the network protocol can have a different impact on the environment. So as much as possible, if we can reduce the amount of information that we transmit through the wire, or the number that we need that we reach the wire, that's the best for our application, and it's the best way to approach the design of an application to reduce the carbon impact that these devices on the network have. The principle number 7 is demand shaping. And this term sounds very similar to another one that we already mentioned, which is demand shifting. We mentioned this on the third principle, and the idea was just to move a workload from one region to another, or from one time zone to another. This is different because demand shaping tries to shape the demand to the supply that we have. And as you could expect, in some regions, let's take as an example a region where during the day there's too much wind. The wind blows, and there's a eolic farm on the region, which produces a great amount of energy. So we can expect to have a low carbon intensity during the day, because the production of energy will be clean. The energy that comes to the grid is clean during the day. At that point, we can just go and have the best performance on our applications, increase increase our features to its best level, and consume maybe a little bit more energy, since we are not having a big impact on the environment. However, as night comes, the wind stops blowing. It's just a hypothetical example. Wind stops blowing, and the production of cleaner energy goes down. So we want to reduce the impact that our application is having based on the production of clean energy that we have on that specific region. And this is important, since we can create carbon aware applications that take into account information of the energy that's coming into the grid, and enable or disable some specific features that could have a higher impact on the planet, on the carbon emissions. An example is video conferencing. Let's say this application that I was mentioning is Zoom, and during the day we can all turn on our cameras and be transmitting in the highest available quality of video. And we will be sending tons and tons of images and video packets throughout the day. However, as night comes, if we still need to use the application, we need to reduce the impact that we're having on the environment. If we stay at the same level, then the company that's producing electricity will need to keep up with the demand, and they will start burning some fossil fuels, and this will be just an issue to this will just be polluting more our region. And one way to achieve this is by enabling eco modes on applications. This is some concept that has been used in other electrodomestics or even in cars, where you let the user decide if he or she wants to sacrifice some performance for a higher efficiency. And this could be the same on applications. We can let the user know that the energy that's coming into the grid is not so clean at the moment, so they can enable the eco mode and reduce or turn off some of the most consuming features that the application has. Okay, so we got to the last principle. The last principle is measurement and optimization. The important idea here is that sustainability isn't a single optimization, but a mind shift when we're observing our application from end to end. There's going to be so much areas that we're tempted to optimize, but we could start by just taking small ones and do some work there. The idea is that it will not be easy, because we also need to choose really wisely the measurement criterion for that specific optimization. We need to set a baseline, then iterate through our optimization, and then check if our work is actually having some impact on what we are trying to optimize. And sometimes it is not so trivial to measure the carbon emissions of an application. We need to find proxies for these emissions, and one example of this proxy is cooling power. Imagine a fleet of servers running for a cloud provider. It's not practical to go and place power meters on each of the sockets where these servers are connected. That will be the best way to measure, or the most accurate way to measure, the power that's being consumed by a specific server. However, that's not actually feasible or not practical. A way in which we can achieve this is by looking at the thermal design power. And the idea goes like this. A server has multiple components, but the three components that consume the most energy out of a server are the CPUs, the memory, and the GPUs. And the hardware manufacturers give on the data sheet this thermal design power, which is a measure in watts. So it is not exactly the power that's going to be consuming the specific power device, but the power that the engineer or the person in charge of creating or designing the data center needs to account to keep the server cool or at the specific temperature and keep it running for long periods of time. So if we take this measurement for each CPU, multiply it by the numbers, and take the power consumption of memory, and also take the power consumption of the GPUs and multiply it, we can have an approximate of the power that's being drained by a specific server on 1 hour. This could actually be expanded at as many hours as we need, but this measurement will give us a rough estimate of the power being consumed by one server on 1 hour. So with this, we get to the end of the 8 principles. I just want to quickly go over the last 4. The number 5 was energy proportionality. Number 6 was network. Number 7 is demand shaping, and number 8 is measurement and optimization. With this, let's go to our next topic, which is serverless. And serverless is a really exciting feature that we have on the cloud. Normally, or the most common way to use a server is by having it on or having it allocated for a specific task the 100% of the time. So serverless is a feature on the cloud that enables us to use the resources only when they are needed. And this has become more and more common on the last few years. Allocating resources only during the execution of the workload could lead to higher utilization on the servers that the cloud provider has. And if we increase the utilization, we also increase the energy efficiency of a specific server, and thus we are starting to use the sustainability principles. Yeah, just as a complement, the why serverless enables the green cloud or a sustainable cloud. Well, carbon and electricity are used more efficiently. Yeah, we have a better utilization, and energy proportionality also increases. And also something that's great is that cloud providers are creating techniques to measure the impact that our applications have. So in this way, if you want to know what's the carbon footprint of your application, or if you're looking to optimize your application to reduce the CO2 that it emits, you can leverage some of these measurement techniques or measurement tools that cloud providers are creating for its customers. We can. I'm gonna show to you some of the serverless products that Azure has. This is just the ones that I've come to use a little bit and the ones that I know. This doesn't mean that Microsoft is the only cloud provider that has serverless services. There's Amazon Web Services also has its own set of serverless products. However, these are the ones with which I'm more familiar, and the ones that I want to show you, so that you can start maybe thinking or building some prototypes of applications leveraging the serverless design principle. So the first one is Azure SQL Database. And SQL Database is SQL Server on the cloud. It has different ways in which you can use it as a customer, but in a rough way, in a high level way to explain it, it's SQL Server running on the cloud, on the Azure cloud, and you can have single databases which scale automatically the compute that they need to process fraud operations. And the benefit of this is that not only the resources will be used more efficiently, but also the billing is changed. So if you're a customer that only needs its compute resources for very specific or very short periods of time, you could actually benefit on the billing side with this serverless architecture. The second one is Azure Functions. And Azure Functions are small chunks of code which are ready to execute some specific operation. The idea is that they are modular and that you can interconnect as many as you need. And the infrastructure will be the one that will scale up and down the resources to account for the demand that you are having at a certain time. This could be used for web APIs. You can react to database changes, or you can receive and process some incoming IoT data streams. The third product that I want to mention is event grids. And these event grids are really useful when you want to subscribe to an event. You set an event as a trigger, and then you will set an event handler to perform some operation. So the event handler could be an Azure function or some other service that Azure offers.
15 minutes, Sebastian.
Yeah, thank you. The fourth one, sorry, is Cosmos Database. Cosmos Database is a non-SQL database which has also a serverless offering, and also has this capability of scaling up and down when you're receiving more or less traffic. And the last one is Logic Apps, which is a serverless engine that helps you connect on-premise solutions with some cloud services. So if you're still having some part of your application running on-premise on your own servers, you could leverage from these Logic Apps to connect to other services on the cloud that you don't have on your personal suite. And just as a real quick example, this is a graph of how serverless would look like on Azure SQL Database. The number of virtual cores used scales up when the demand increases, and once the demand is reduced, the infrastructure will reclaim these resources and they will scale down automatically. You as a app owner, you don't need to do anything at this moment, and that's actually beneficial to both to the efficiency of the way the resources are being used, and also to the billing that you have for this service. So with this, let's go and see how serverless can use some of the sustainable software engineering principles to create an app. And this application is from a company, a car insurance company called Contoso, and we're moving from an on-premise solution to a cloud solution. This Contoso company wants to find a solution with the lowest carbon footprint. So they heard about serverless and they want to use this technique to be more efficient with the use of resources and help the environment in some way. So right now they have everything on their own servers. They're running a customer side which receives some pictures of the problem that a car has with the license plate of the car, and the customers need to upload these images to a cloud storage. They also own some GPUs which are running, and they extract the information from the images and start the claim processing on the backend. So let's see how this company migrates to a cloud solution using some of the Azure services and products that I mentioned. So first of all, we will have this front end part of the application, which needs it needs an application. It needs a user interface so that the customer can take some pictures and analyze the information that's on them. For this, we will use Azure Cognitive Services, which has a serverless computer vision API. This API is serverless because you will only be charged for the number of calls that you do to the API, and it will scale depending on the number of requests that you get on a specific period of time. This serverless, the information that's extracted from the Azure Cognitive Services will be posted into an Azure function. This Azure function will be in charge of storing the image into a blob. All of the vehicle images will be stored here, and at the same time we have an event grid that's subscribed to the event of uploading an image to that storage. So this event grid will trigger once you upload the images, and the backend will come in and will start doing the claim processing. So the first thing that we need to do on the backend is store some of the information that we already gathered. We need to store the metadata of the car that we're gonna process, and it goes into non-SQL database, which will leverage Cosmos DB serverless. Once this information is stored, we can proceed into the queue of the claims. We will create a queue to start the backend processing, and we will have two different queues. One of them is the priority processing for those customers that need information about their claim right away. This will go through an HTTP pipeline and hit directly the master database, which is a SQL database with all the information about claims and history about the customer, history about like pricing tables of the cars. Everything will be stored here, and that will be only for those customers that need an actual immediate response. However, claim processing not only can be not always can be treated as a priority task. Sometimes it requires information from different areas of the company. Some expert needs to consult with it. So those claims that do not apply for the priority processing will go into a storage queue. And this storage queue is follows a design pattern called delayed compute, where you will let the customer know, you will let the user of the application know that he or she will receive a response in a certain period of time, and you then will start doing all of these requests to the different areas. And once you gather all the information that you need, you can actually go and see if the claim is approved or rejected by hitting the master database, which is the claim storage database. The key idea here is that delayed processing, well, besides the serverless pattern that we're following with all of these products that Azure has to offer, delayed processing is also a sustainable design pattern in which you can maybe use demand shifting and move it from one place to another, or delay it till, if you have a large number of claims, you can delay the processing of these claims to later in the day, or move it to a different region if possible. And this will actually improve the carbon footprint of the application. So with this, I want to finish with two philosophies that are the foundation of the sustainable software engineering. These philosophies are: the first one is that everyone has a part to play in the climate solution. People that's interested in sustainability and that works in technology is scattered around companies in different areas. They go all the way across designing silicon, designing chips, to creating better user interfaces or user experiences. So the idea is that everyone, no matter where you are, you could choose a subset of the principles and start applying them on your daily tasks. Small changes here and there are the ones that are gonna lead to big changes at the end of the day. And the second philosophy of sustainable software engineering is that sustainability is enough all by itself to justify our work. You can find multiple reasons. There's cheaper solutions. Once you start optimizing, you're gonna be more performant, more resilient. But the primary reason why we do this, why sustainable software engineering exists, is to be more sustainable, to have a positive impact on the environment and reduce the carbon footprint that we are having into the environment. With this, I'll leave this this amazing site, which is totally open source. People from different companies from different areas are contributing to this project, and it is called principles.green. You can go check it out if you want to learn a little bit more about each of the principles. You can also investigate here more design techniques that you could leverage on your day-to-day work to improve the carbon footprint of your applications. And with this, I want to thank everyone for your time for this almost 60 minutes, and hopefully you'll get a little bit more interested on sustainability, on green design techniques, and feel free to reach out to me if you have any questions, or if you have them now, please go ahead and let me know. But that's it from my side, and thank you very much.
Thank you very much for that session. It gave me a lot of food for thought. And there are no questions, but I have one. And what's
Sure.
your opinion on Bitcoin?
Wow, that's a hard one.
From an energy perspective.
From an energy perspective, okay. It has some. If you I haven't thought about that very deeply, but it's actually not very, it's not really efficient what we're doing right now, as the number of possible Bitcoin tokens like decreases. We're like just using more and more energy in a useless way, because at the very beginning, people was just farming Bitcoin, and they could actually get something out of it. But right now, it's almost like much of the energy that's used to farm it, it's just like being thrown away. So I hopefully there's a finite amount of tokens, I think. So hopefully at some point we can modify the way in which we use these resources, because it's having a really high carbon footprint on the environment.
Yeah!